picture this. You're watching a classic movie, maybe an old Western, and a stagecoach is speeding across the screen. But when you look at the wooden wagon wheels, they seem to be spinning backward.
Yeah, or like those videos of a helicopter taking off,
Oh, right.
where the rotor blades look completely frozen in midair. Like the thing is just magically levitating off the ground.
It's a total optical illusion. I mean, it's something we have all experienced at some point. But today, we're going to look at exactly why your eyes and your brain are being so thoroughly fooled. Welcome to our deep dive into the fascinating physics and math behind this illusion.
Because in the engineering world, this isn't just a neat trick. It's known as kinematic aliasing.
Right.
And it is a phenomenon that feels like a glitch in the matrix. The reason we're doing this deep dive today is because we have a really fascinating piece of source material to unpack.
We do.
It's an engineering note titled Relative-Ratio Bookkeeping for Kinematic Aliasing. And it was authored by André Dupke of Scale Time Dynamics.
And I have to mention their logo before we even get into the weeds here.
Oh yeah, it's great.
It is this incredibly striking black circle featuring a very crisp white Greek letter sigma with a subscript O, very sharp, very mysterious.
It really is.
But getting back to the paper itself, what is the core mission of Dupke's work here?
So the mission of this deep dive is to explain why these visual paradoxes are actually, at their core, an unsolvable mathematical limit.
Unsolvable.
Unsolvable. That is, unless you use some very specific engineering cheat codes, we're going to unpack why fixing this illusion isn't about finding some, magic software algorithm.
Right.
It is entirely about making the right physical assumptions about the world you're observing.
So for you listening, whether you're working in machine vision, doing rotor diagnostics for a living, or you're just insanely curious about why your eyes play tricks on you on the highway.
Which happens to me all the time.
Exactly. This deep dive is going to completely change how you look at periodic motion. You will honestly never look at a spinning wheel the same way again.
Definitely not.
So let's start with the foundation. The author introduces a concept called the normalized phase advance variable. In the paper, it's denoted by the Greek letter nu.
Yeah.
How does this change our standard approach to measuring speed?
Well, the most important thing to grasp here is the unit of measurement itself. It is measured in cycles per sample.
Okay, so not like RPMs.
Exactly. Instead of measuring speed in standard continuous units like radians per second or rotations per minute, we are looking at how many full rotations happen between each discrete snapshot or frame of our camera.
So it's tying the real-world motion directly to the camera's frame rate?
Precisely. It combines the physical continuous rotation rate and the sensor's discrete sampling rate into one single normalized number.
Okay, that makes sense. The paper then introduces the concept of the wrapping map.
Right.
And since a digital sensor is taking discrete snapshots rather than recording continuous reality, any motion that exceeds a certain threshold between those frames just gets tangled up.
Yeah, and what's fascinating here is the threshold itself.
The half rotation thing.
Yes. If the movement exceeds half a rotation, which engineers call the Nyquist limit between frames, the observation gets wrapped.
Rad.
The camera is blind to the time between the flashes. It only registers the phase angle of where the wheel was and the phase angle of where it ended up.
Okay, the paper gives a highly specific example to illustrate this, which they label Demo 1.
This is where it gets really clear.
Let's walk through it. Imagine a wheel spinning at a true speed of 2.7 cycles per frame.
Okay.
So between frame 1 and frame 2, the wheel completes 2 full rotations plus 0.7 of a third rotation. Walk us through what the camera actually calculates in that scenario.
Well, the camera fundamentally cannot see those 2 full rotations.
Because the shutter is closed.
Exactly. It only registers the leftover fractional phase difference. The math Dupke uses is elegantly simple here. You take the true speed of 2.7, and the wrapping map subtracts the nearest whole number of rotations.
Which in this case is 3.
Right. So the calculation is 2.7 minus 3, resulting in negative 0.3. The camera records an apparent speed of negative 0.3 cycles per frame.
So to your eyes, looking at that discrete data, the wheel appears to be spinning backward.
Backward by 0.3 cycles every frame.
Okay, let's unpack this. The observed speed of negative 0.3 cycles per frame is what the sensor spits out. But the core thesis of Dupke's paper is that this single data point is functionally useless on its own.
It really is. Because that observed speed of negative 0.3 is mathematically identical to a true speed of 0.7.
Or 1.7.
or 2.7 or 3.7. The list goes on forever in both directions.
It's an infinite set.
An infinite set of uniformly spaced possibilities, which engineers call aliased branches.
So if a computer, or your brain for that matter, is handed that single piece of wrapped data, no algorithm in the world can calculate the true speed.
None. The author emphasizes that aliasing isn't just noise or distortion that you can just filter out in post-processing.
Right.
It is a fundamental loss of injectivity.
Loss of injectivity. I haven't heard that term since college math.
Right. In mathematics, an injective function is a one-to-one mapping. Every output traces back to exactly one input.
But aliasing destroys that property.
Completely. Multiple different physical realities map to the exact same observation. The original data regarding the integer number of rotations is literally gone.
Just erased.
Completely erased by the discrete sampling process.
Which leads to the massive engineering takeaway of this first section. Treating alias correction as a universal inversion problem, acting like you can just run a clever math equation backward to find the true speed, is a deeply flawed paradigm.
It's a massive mistake. You must supply extra outside information to solve it.
You need a cheat code.
You do. You cannot reduce that infinite list of possibilities without bringing in an external physical constraint or assumption to break the mathematical symmetry.
That perfectly sets up the solutions, because the author pivots to propose 4 distinct disambiguating assumptions. Let's look at method A first, which the paper calls known start continuity.
Okay, so the assumption here is that you know for a fact the machine starts from a sub-Nyquist state.
Meaning, it starts from 0.
Or at least from a speed slow enough that the camera captures it without wrapping, and it accelerates smoothly enough that the phase advance between any 2 consecutive frames never jumps by more than half a cycle.
So in Demo 2 of the paper, they show a motor spin-up tracking a true speed starting at 0.1 cycles per sample, and it smoothly accelerates up to 3.5 cycles per sample over 200 frames.
Right. And because the software tracks the continuous history of the movement from a known sub-Nyquist origin, it continuously updates the integer wrap count.
It essentially unrolls the map as it goes.
Exactly. It unrolls the map.
But what happens when the physical machine violates that smooth continuity?
Well, this method has a highly specific and catastrophic failure mode. It's detailed in Stress Test 3.
I read that part. It completely breaks down.
Yeah, they simulate a scenario where the motor's speed jumps abruptly by 1.6 cycles per sample between 2 frames.
And since the algorithm expects the change to be bounded within half a cycle,
When it sees a jump of 1.6, it interprets it as an alias jump of negative 0.4.
the software essentially jumps onto the wrong mathematical branch.
And because method A relies entirely on its own historical integration, every single subsequent estimate inherits that initial branch error.
So the tracking is just permanently derailed.
Yep, derailed until the system returns to a known sub-Nyquist state to reset.
Okay, so if method A fails catastrophically during an abrupt speed jump, how do we handle a system that doesn't start smoothly or has highly dynamic acceleration?
That brings us to method B.
Method B. The paper calls this bounded 2-rate congruence.
The best way to visualize this is observing a high-speed rotor through 2 different unsynchronized sample rates.
So like looking at a spinning wheel through 2 different strobe lights?
That is a perfect analogy. It is a multiple sample rate approach that leverages modular arithmetic. The paper outlines this in Demo 3.
Walk us through that demo.
Consider a true physical frequency of 81 Hz. We sample this continuous signal with 2 separate discrete sensors, one operating at 30 Hz and one at 31 Hz.
So looking at the 30 Hz camera alone, you get a highly aliased ambiguous reading.
Right.
And the 31 Hz camera gives you a completely different, yet equally ambiguous aliased reading. Both are individually useless for determining the true 81 Hz speed.
But here is the mathematical cleverness of method B.
Yeah.
You essentially have 2 different infinite lists of possibilities.
With 2 cameras.
Exactly. But if you impose a physical boundary, say, the motor's absolute maximum physical speed is bounded at 150 Hz,
Yeah.
you can execute a bounded 2-rate congruence search.
You cross-reference the 2 sets of alias data within that specific 150 Hz window.
Yes.
And here's where it gets really interesting. It's basically an application of the Chinese remainder theorem.
It is.
Because the 2 cameras are sampling at different rates, their aliased branches drift apart. There will be exactly one speed within that bounded range where both cameras' observations mathematically align.
It seamlessly recovers the true speed of 81 Hz without needing a sub-Nyquist known start.
But method B sounds like you are doubling your hardware costs for a mathematical edge case. I mean, 2 cameras. what are the practical failure modes of relying on dual sensors like that?
The failure mode here happens in two distinct ways. First, if your maximum operational boundary is too loose.
Like if you set the search limit to 10,000 hertz instead of 150?
Exactly. The mathematical branches will eventually cross again, finding multiple speeds where the observations aligned, which throws you right back into ambiguity.
And the second failure mode.
It fails if your two sample rates share a large common factor. You need the sample rates to be relatively prime to maximize the distance between those mathematical overlaps.
So if both cameras sample at multiples of 10?
Their aliased errors will overlap constantly. It defeats the whole purpose.
Okay, let's move to method C, fiducial timing. Out of all the complex numerical analysis in this paper, this one is a stark departure. It sounds almost primitive.
It is brilliantly simple.
You introduce a physical asymmetry to the rotor. You machine a notch into the shaft or place a highly reflective marker, literally a sticker, on the wheel.
If we connect this to the bigger picture, the brilliance of method C is that it completely sidesteps the mathematical paradox we just spent all this time detailing.
It just bypasses the aliased phase stream entirely.
Yes. You are no longer attempting to calculate the wrapped phase advance between discrete frames. You're simply performing direct time of flight or period measurement.
You record the timestamp when the sensor detects the fiducial mark, and you record the timestamp when it detects it again.
And the inverse of that time difference gives you the true frequency. It's completely immune to any wrapping ambiguity.
It is the ultimate physical intervention to bypass a discrete sampling limitation.
Right.
But looking at stress test 4 in the appendix, the vulnerability here is entirely environmental, right?
Totally environmental. What happens if optical glare obscures the fiducial mark during a rotation?
Or dirt gets on the sticker.
Exactly. The vulnerability is known as marker dropout. If the sensor misses the fiducial mark even once due to noise, glare, or dirt, the system records the time for 2 full rotations, but calculates it as a single rotation.
Oh, wow. So the algorithm assumes the rotor is spinning at exactly half its true speed.
It introduces a massive ratio error. Your data integrity is entirely bottlenecked by the physical detection consistency of that single marker.
Okay, that leaves us with the final assumption, method D, external coarse prior. This is essentially a classic coarse-fine sensor fusion approach.
We call it the wingman approach.
The wingman sensor, I love that. So you pair your high-precision optical sensor with a low-fidelity secondary instrument to establish a baseline.
And you don't need the secondary instrument to be precise at all. A cheap tachometer, a crude uncalibrated accelerometer, or even an expected control command value is sufficient to resolve the integer ambiguity.
The paper illustrates this in Demo 4. Going back to our first mathematical example, our primary optical sensor gives us a highly precise but wrapped reading of negative 0.3 cycles per sample.
Right.
We know that equates to an infinite set of branches. But our coarse wingman sensor dictates that the speed is somewhere in the neighborhood of 2.75.
The coarse sensor provides an unambiguous, albeit noisy, prior.
So by fusing the highly precise but ambiguous fractional phase of negative 0.3 with the imprecise but unambiguous integer prior of 2.75.
The system snaps to the nearest logical branch, locking onto the exact true speed of 2.7.
That's incredibly elegant, but how accurate does that coarse prior actually need to be to prevent the system from failing?
The tolerance is strictly defined by the wrapping map itself. The prior estimate must be accurate to within half a rap of the true speed.
Half a rap. So if the true speed is 2.7, but your cheap secondary sensor drifts and reports a prior of, say, 3.4.
The algorithm will fuse that bad prior with a negative 0.3 reading and snap to the nearest mathematical branch, which is 3.7.
It locks onto a completely false reality.
With absolute mathematical confidence, which is the most dangerous kind of error.
Wow. So what does this all mean for someone actually building one of these systems? Say, a machine vision engineer building a high-speed drone or an automotive engineer tracking wheel slip. What is the optimal architecture?
The author makes a definitive recommendation in the conclusion. For real-world systems operating in dynamic environments, the most robust architecture is a combination of Method D and Method A.
Fusing them together.
Yes, Dupke calls this prior-seeded tracking.
Okay, so you utilize the coarse-fine sensor fusion just to find the starting speed branch, resolving the initial ambiguity.
Exactly.
And then once you are locked onto the correct integer branch, you rely on Method A's continuity tracking to follow the motion smoothly from there on out.
It is highly efficient. It doesn't require machining physical fiducial markers onto every single moving part, and it avoids the complex synchronization and computational overhead of bounded two-rate congruence.
You just need one credible week prior to seed the system initially, and then the continuous phase tracking handles the high dynamic maneuvering.
And the paper backs this up with heavy technical rigor. The appendices contain the Python reference implementations.
I saw those. The scripts named stipdelias.py and stipdeliasrobust.hi.
Dupke didn't just outline the mathematical theorems. The appendices detail synthetic validations and robust stress tests dealing with real-world sensor realities.
Because in theoretical math, everything works perfectly. But those robust stress tests address a critical flaw. Real-world sensors drop data.
Packets are lost in transmission. Frames are dropped by the buffer.
And when tracking wrapped phase data over time, missing a frame introduces a severe interpolation challenge.
Severe is putting it lightly.
Because you cannot simply draw a linear average to guess what the phase was during the missing frames.
You absolutely cannot. The author dedicates a significant portion of the appendix to a technique called phasor-safe interpolation.
Phasor-safe interpolation.
When dealing with wrapped phases, the numerical value is artificially bounded, usually between -pi and +pi radians, or -0.5 and +0.5 cycles.
Right. So if your phase is at +0.49 in frame 1 and wraps to -0.49 in frame 3,
A standard linear interpolation for the missing frame 2 would just average those numbers together and guess 0.
which implies the rotor completely stopped and reversed direction in a fraction of a millisecond.
Which is physically absurd. The linear math completely fails at the discontinuity.
So how does the Python script in the appendix actually resolve that boundary jump?
It maps the discrete, one-dimensional phase data onto a two-dimensional complex unit circle.
Okay.
Instead of tracking the raw numerical phase, the script converts the phase angle into a complex number using Euler's formula, separating it into real and imaginary components.
I see.
The interpolation is then performed independently on the continuous real and imaginary coordinates.
That is so smart. By moving the math into the complex plane, you bypass the artificial discontinuity of the wrapping map entirely.
Exactly. You bridge the missing data across the boundary jump smoothly, and then you just calculate the angle of the interpolated complex number to get the corrected phase.
It is a phenomenal layer of technical rigor. It prevents the prior seeded tracking algorithm from collapsing the moment a camera buffer stutters.
But, pulling back from the Python code, the most profound takeaway of this entire engineering note is the overarching philosophy Dupke outlines in the conclusion.
Yeah, the text explicitly states that spending engineering cycles asking which de-aliasing algorithm is mathematically superior is the wrong approach entirely.
It is not a software problem.
It's a hardware problem.
It is fundamentally a sensing strategy problem. The right question an engineer must ask is, which disambiguating information source is physically available and reliable in my specific hardware architecture?
Can you guarantee a sub-Nyquist startup?
Right. Can you ensure relatively prime sample rates across multiple clocks?
Can you guarantee a clean optical path for a physical fiducial mark?
Or do you have access to a secondary data stream for coarse fine fusion?
It reframes the entire paradox. It takes kinematic aliasing from being this mysterious optical illusion or an annoying artifact of digital sampling, and it turns it into a rigorous, assumption-driven bookkeeping problem.
Knowledge is most valuable when understood and applied at the architectural level. This framework forces engineers to stop trying to cheat Shannon-Nyquist sampling theorems with software alone, and instead design systems with the necessary physical constraints from day one.
So, to summarize our deep dive today for you listening, that backward spinning wagon wheel on the screen isn't a glitch in the fabric of reality.
Not at all.
It is a fundamental loss of injectivity in the discrete sampling of the camera. The data of the true integer speed is completely erased, leaving only wrapped fractions.
And the only way to crack the code is to break the mathematical symmetry by bringing outside physical context into the equation.
Whether that's known sub-Nyquist starts, dual-rate congruence, direct period measurement via markers, or an external coarse prior.
The mathematics are unyielding unless you provide the key.
Exactly. So the next time you are driving down the highway and you look over and see a car next to you with hubcaps that look like they are slowly spinning backward, you now know exactly why your brain can't solve the math. Your visual cortex is discrete, and you are lacking an external prior.
This raises a really important question, though, and it's something I want to leave you with today.
Oh, lay it on us.
If our own human eyes and brains suffer from this exact same discrete sampling limitation, if we can be completely fooled, locking on to false physical realities just because of the biological frame rate of our visual cortex processing.
Yeah.
What other massive continuous motions in the universe are we completely misinterpreting right now, simply because our instruments don't have the right fiducial marker to see the truth?